Hello everyone, welcome back to another mini concept, this time about equilibrium expressions and constants. So equilibrium expressions are another way to, or not another way, are the way for us to numerically express how equilibrium exists within a reaction. In the sense that equilibrium can either be product favored or reactant favored. And what does that mean? We'll get into that later. First, let's review what we know about just expressions and constants themselves in terms of rates because they're actually quite similar. Now, for let's say a reaction given A and B as the reactants convert completely into C and D, the rate of, for example, A, the rate of disappearance of A would be the whatever the coefficient is. So let's just write their coefficients here. It would be 1 over the reciprocal of its coefficient, 1 over the coefficient rather, multiplied by the change in concentration of A over the change in time. Now, since it's a reactant and it's being consumed, we make this negative, right? Now, this is an example of a rate expression. Now, we also have in kinetics what we call the rate law, and the rate law is given as the rate constant multiplied by the concentration of, let's say, A and the concentration of B with their respective orders, right? So, why does this matter? We can see that constants and expressions are both common in these two concepts. Now, in rates, we use the expression to show how fast it's changing. Here in equilibrium expressions are there to show the ratio of product concentrations to to reactant concentrations. These allow us to illustrate which parts of the reaction actually affect the equilibrium. They allow us to put a number to it. Now, how is it written? So, an equilibrium expression is given by the concentration of products to the coefficient of the products. So let's say that we have also let's just complete it. It's over the reactants to the coefficient. So let's say we have again A plus B is reversible to C and D. The the equilibrium expression would be, let's give them numbers. Let's give this 2, let's give this 1, 3, and 4. So on the top, it would be A to the power of 2 multiplied by B to the power of 1, or just B, over C to the power of 3 and D to the power of 4. Now, this is just the expression. What does the expression solve for? The expression solves for what we call the equilibrium constant. Equilibrium constant, which is given by capital K. So keep this in mind. Capital K is equilibrium constant. If you're given small k, this is the rate constant. Now, for this, k can have multiple meanings. And also, k is expressed in different ways. But first, let's just go over what this expression means. So, in this expression, we can see that we're comparing our products on the top and our products on the our reactants on the bottom. Let's say that, just for understanding, let's say that this totals to 3 and the bottom totals to 2. This means that for every 3 moles of product, 3 moles of product, there's going to be 2 moles of reactant at equilibrium. So basically, it's saying that at equilibrium, there's going to be more product, right? And why does understanding this help us, right? This helps us understand how K behaves, right? So, regardless of if it's KC or KP, which we'll get into in a bit, the interpretation actually remains the same. So, when K is greater than 1, such as here, 3 divided by 2 would equal 1.5. this means that it's product favored. Now, how about if it's less than 1? So let's say that our expression gives us 1 over 2. So that means that for every 1 mole of product, there's going to be 2 moles of reactants. This would simplify to 0.5. Now, what do we do if K is less than 1? This means that it's going to be reactant favored. Let's just shorten this. Reactant favored. And of course, if they're 1 to 1, that means if K is equal to 1, that means that they exist, well, equally. Their concentrations are equal. So it's just equally favored. Essentially, 1 mole of product will appear for every 1 mole of reactant. Now, like I mentioned earlier, so we're just gonna leave that up there, right? We're just gonna leave this here so that you guys can take a look as we go through our examples. There are 2 types of equilibrium constants which we will talk about today. First is Kc. So Kc is the concentration constant, or the equilibrium constant of concentration. Now, what is this given by? It's the exact same thing. So it would just be literally this expression, because we're dealing with concentration, right? So what we actually solve for here, what we got here is Kc. Now, how about if we specify their states, right? Let's say that A here is a gas, B is a liquid, C is a solid, and D is aqueous. Right? Now, when we're dealing with equilibrium constant of concentration, we do not include liquids and solids. We also don't include solvents, but that's besides the point. So, for liquids and solids, the reason why we don't include them is because liquids and solids are given by, their concentration is given mostly by density, right? And what's the difference between liquid and aqueous is that pure liquids are, again, determined by density, and aqueous solutions are given by molarity. Here, the concentrations are always going to be given in molarity, right? So, given that we don't include liquids and solids, those 2 should not be included. Therefore, our new Kc expression would be, where we cross these 2 out, it would actually just be A to the power of 2 and D to the power of 4. Their concentration to the power of 2 and 4 respectively. Now, how about if we're dealing with Kp? What is Kp? Kp is partial pressure. Sorry, this shouldn't say product. This is partial pressure. There. Now, this is just the same formula, except it only applies to gaseous parts of our reaction. So since here we only have one gaseous element, which is A, Kp, let's change the color. Kp, let's make this green. Kp would be equal to, do we have any gaseous elements on the right side? We don't, so it will be 1 over, again, B won't be included because it's a liquid, so the partial pressure indicated by P of A to the power of 2. This is our Kp expression. Right. Now, again, Kc and Kp both follow these rules. So Kp or C, P or C, P or C. Now, that's how we interpret it, right? So, let's try a simple example. Let's say, hold on, let's zoom in a bit. So let's say that we're given at equilibrium, consider the reaction. Let's just go with another A and B, just a simple one. Say A and B is reversible to C, and This is 2, 3, and 4. A is aqueous. My handwriting sucks. Aqueous. They're all aqueous. Alright, so first let's write our equilibrium expression for Kc. Find Kc and Kp here if applicable. So for Kc, we just have to write Kc is equal to first the concentration of the right side. So let's say that they're just 4m, 3m, 2m respectively, right? So that it's easier for us here just for demonstration purposes. So let's say that we have on the right side 4 moles 4 molar of C. That means on top we would have 4 to the power of whatever the coefficient is, which is 4 over A. Rather, the concentration of A is 2, so let's put it there. 2 to the power of 2 times B, which is 3 molar, to the power of 3. So if we simplify this, hold on, let me bring on my calculator. So 4 to the power of 4 divided by should get us 108. So how do we interpret Kc? Kc basically says that the Kc is 108 and 108 is greater than 1, thus it's going to be product favored. Product favored. There. Now that means that for every complete set of the left side, we produce 108 of the right side. Well, that's a gross oversimplification, but you guys get what I mean. It's the ratio of the product to the reactant. Now, how about Kp? Is Kp applicable in this situation? Do we have any gaseous elements or compounds? We don't. Therefore, Kp is Na. This time, let's try something else. Let's have another reaction. So at equilibrium, or rather let's change our color. At equilibrium, why is it so ugly? There, at equilibrium, 2A plus 4B is reversible to C. Okay. Now its concentrations are 1m, 2m, and 3m. And we're looking for Kp and Kc. This is gaseous, this is aqueous, and this is gaseous. Alright, so now just take this imaginary reaction, right? Just for demonstration purposes again. Let's try and find Kp and Kc. So this time, let's start with Kp. Since a while ago we started with Kc. We have to find our gaseous product, the concentration of our gaseous product, and put it on the top. Alright, so our concentration of our gaseous product, which is C, is 3m. To the power of its coefficient, which is, well, 1. So we'll just we'll make it to the power of 1 and just leave it there. 3m. Now how about on the left side? What are our gaseous reactants? We have A, and the concentration of A is 1, so we'll have 1 molar to the power of 2 because of its coefficient. Now this would simplify to 3. So our Kp is greater than 1. That means it's product favored. Now how about Kc? So for Kc, Kc is equal to the concentrations of, well, everything here, because we don't have any pure liquids, pure solids, so we can use all of the data that's given to us. So again, on the top we would have 3m to the power of 1. On the bottom we'd have 1m to the power of 2 multiplied by 2m to the power of 4. So this would equal 3 over 16 which is going to be that's going to be less than less than hold on, less than 1. So Kc is less than 1. Now, what is their relationship here? Well, Kc takes into consideration the concentrations of gaseous and aqueous. So basically, it's saying here that this is going to be reactant favored, right? Now, instead of it being product favored like the gas is, we're comparing concentration here. So there's more just generally reactants on the left side rather than there are the products. Now, product favored is the partial pressure equilibrium constant because the right side or the product is primarily gas, and because it's primarily gas, we obviously expect there to be more moles of gas on the right side since we're converting the reactants into a gaseous product, right? And there's actually a relationship between Kp and Kc. So this is the last part of this video. Now, the relationship between Kp and Kc. Kp is given by the product of Kc by the gas constant, the temperature at equilibrium, and the change in moles, right? The change in moles of gas. Now, how about Kc? Well, obviously here we just have to alter this equation a bit, so we're just gonna divide Kp by this. So our Kc equation would be the equilibrium constant of partial pressure divided by RT to the power of the change in moles. Now, what is R? What are we using here? We're using 0.0821 liter atmosphere. There. So that is another relation for Kp and Kc. So let's try that just with a really, really simple example. So let's say given Kc is equal to let's say 4 at 300 Kelvin. So this is temperature in Kelvin, by the way. Temperature in Kelvin. And the change in moles is equal to 2. What is going to be our Kp? So we just have to plug and play our values here. So that's 4 times 0.0821 times 300 Kelvin to the power, the result of this, all to the power of 2. So now let's try that in our calculator. So that's 300 times 0.0821. Now we square the result and we multiply it by 4. So our answer here is going to be 2000, or rather, so that we can keep our significant figures here, let's keep it at one significant figure. We'll have 2 times 10 to the power of 3. And that's going to be our Kp. If you want to go the opposite way, well, eventually we can get Kc, right? Now, that's it for this video. I hope you guys learned something. And again, equilibrium constants and rates are actually quite similar to rate. Equilibrium expressions and rate expressions are quite similar to each other, and they function in different ways, but they're formed based on, again, the products and the reactants. Now, I hope you guys remember how these formula work, particularly what to omit in these formulas. Again, for Kc and Kp, for Kc first, we do not include pure solids and pure liquids, and for Kp we only include gaseous elements or gaseous constituents for our reaction. And Kp and Kc are related to each other by the following equations, and that's it. I hope you guys learned something, and I'll see you guys in the next video about reaction quotients, which will allow us to predict the behavior of the reaction as it approaches equilibrium. So thank you, everyone. and goodbye.